The next lecture is going to be on policy gradients and actor-critic methods, lecture 4A. Lecture 4B will be on the same topic from a different perspective, and there is a reason for this. A lot of the current successes in reinforcement learning are through policy gradient methods. The math is quite a bit different from what we've seen so far, so it's nice because you can a little bit start from scratch, but also there's going to be a lot of new things to absorb, and I'll cover it from a mathematical perspective. Andre will cover it then from a more programming perspective, and then later in John's session at the end here, you'll see a lot of nuts and bolts relate to policy gradients. So let's remind ourselves of where we're at. We're doing reinforcement learning. Our agent's supposed to somehow learn to act in this world, take actions which will now be UTs instead of ATs, slight change in notation. Action UT is taken, things change, new state, reward associated with what happened, agent faces that, decides again, and this keeps going around. And what we're going to look at in this lecture is this part of the puzzle, policy gradients and actor-critic methods, which are direct policy optimization methods rather than dynamic programming methods. Everything we've seen so far are dynamic programming methods, which try to get a self-consistent set of equations satisfied for the Q values or for the V values. It's going to be very different now. So the goal here will be to find a policy pi theta, which is now going to be stochastic in entirety of this lecture, distribution over actions given state that maximizes expected sum of rewards. Ultimately, that's what we care about, finding such a policy. Thus far, we've done the search for such a policy in a very indirect way, finding a value function or a Q function, and then from that, having a policy. Now we're just going to see if we can directly find a policy that can do well. The way to think of the policy would be some neural net that processes maybe some pixels or state information, processes it through a few layers, and then outputs a distribution over possible actions that you might want to take. Then to act, you'll sample from that distribution, see what happens, process repeats. Okay, so the parameterization of our policy, for concreteness, we'll think of it as a big neural net, and so the theta vector now used to be encoding a parameterization of a Q function. Now theta parameterizes the policy. That is, the weights in the neural net are the theta vector, and this is our policy. We still want to maximize expected sum of rewards. We're actually not going to discount in this lecture. So gamma equals 1. We're just going to maximize expected sum of rewards, and we're going to use a stochastic policy class, meaning the policy class is the set of policies that we'll choose from, and we hope that in that set there will be a good one that we'll find. There's a few reasons to use a stochastic policy class. Maybe the most important one is that it smooths out the optimization problem. Because what are we trying to do here? We're trying to find a policy that maximizes expected sum of rewards. If we have a deterministic policy, let's say in a grid world, changing an action is a big change. Changing action in a state can have a very significant change on the outcome. It's not a very smooth thing to do. But once we have a distribution over actions in every state, we can slightly shift the distribution, and that will only slightly shift the expected sum of rewards. And so thanks to having a stochastic policy, we have a smooth optimization problem, and now we can maybe apply some kind of gradient descent on this optimization problem to find a good, at least local, optimum of this problem. So why policy optimization? Often the policy can be simpler than the Q value or the V value. For example, let's say you need a robot to grasp something. It could be as simple as having the gripper go somewhere and close around it. And that conceptually is maybe not that difficult, but if you wanted to learn a Q value or a V value, you would need to learn exactly numerically how much reward is associated with that process, which means that you need to understand exact timing, you need to understand exactly how robust that grasp is, and so forth. If you just learn a policy, you don't need to worry about all those details, and so maybe it's simpler because you can just focus on the essence. Another reason you might want a policy and not a V is that V does not prescribe what actions to take. Once you have V, you still need a dynamics model, a transition model, to understand what action you should take in the current state. If you learn Q, but it's a high-dimensional action space or a continuous action space, computing this argmax can be tricky. Because even when you know what the Q values for every state and action combination, maybe encoded in your neural net, how are you going to know which action to take? In DQN, which you saw Vlad present, it's not too hard because it's one output per action, and you can see which one has the highest score. You can take that one. But if you have a continuous state action space, continuous actions, you cannot have one output per possible action because there's infinitely many actions you could take. So we need then to take the action as an input, most likely. Input is action and state. Output is the value of that action-state combination. Now, you need to solve an optimization problem that could be pretty difficult to solve to know what action to take that maximizes Q values. Question, yes? So good question. So the notation in reinforcement learning, there is notation for actions. Sometimes people use A, sometimes U. For state, sometimes X, sometimes S. And it turns out when it's direct optimization, often U is used, and so I'm using that here. But ultimately, you could use A, and the math would all be the same. It's just what people are familiar with in this context is usually U. Let's dive a little deeper in terms of the differences. Policy optimization, you optimize directly what you want, what you care about. You're going to optimize a policy that maximizes expected sum of rewards. If you do dynamic programming, let's say you learn a Q function, you run DQN, you learn a Q function that tries to satisfy the Bellman equation. But if it doesn't satisfy it, which typically will be the case, it'll be some approximation. It's not clear how much you're losing, and you're not directly optimizing for what happens when you use that Q function to then act. Here, when you directly optimize your policy, you directly optimize the objective that you want ultimately. Another reason you might want policy optimization is that it's more compatible with rich architectures, including recurrent architectures, often easier to work with. Hard to know now, but that's just some foreshadowing. It's more versatile. It's easy to set up a policy and just work with it. With Q values, it can be harder. And it's more compatible with auxiliary objectives. Then the nice thing about the dynamic programming methods, and especially Q-learning that you don't get here, is more compatible with exploration and off-policy learning. Exploration is finding parts of the space you haven't been to and learn about them. The methods we'll see here in policy gradient methods will be on policy. You need to act with your current policy and then improve it gradually. Whereas in Q-learning, you can have a separate data collection policy from the Q-learning, and that's fine. Your data collection policy can be very exploration-oriented, which can be beneficial at times. So that's the difference between on-policy, off-policy. How you collect your data in on-policy is directly tied to your learning, and off-policy, you can collect your data whichever way you might like. Often, dynamic programming methods are more sample efficient because they look at more details of the problem, use that Bellman equation, can use the data more efficiently. Doesn't mean they're more computationally efficient because you might need to do many updates on the data to actually take advantage of it, but they're often more sample efficient. So there are some trade-offs here, and both are worthwhile. I would say typically the policy optimization methods are easier to get to work. If you're just going to try one thing on a problem, it's probably the thing you would try first and see what happens. The gradient we're going to use is a special kind of gradient, a little different probably from the gradients you're used to. It's called the likelihood ratio gradient, in this case a likelihood ratio policy gradient, and we're going to derive it. So, more new notation. Tau will denote a state action sequence. So state at time 0, action at time 0, and so forth till horizon h. That entire thing we'll call tau. We'll associate reward with the entire trajectory, which is the sum of the individual rewards along the trajectory. And the utility of a policy with parameter vector theta is the expected sum of rewards, and we can write this as sum over all possible trajectories, probability of that trajectory under the policy times the reward associated with that trajectory. So in this new notation, which we're using for compactness, we're losing some structure, but we get more compactness, easier to think about this. We maximize utility as a function of policy parameter vector theta, and that means that we're maximizing this expectation here. Okay, we're going to do some math here to derive the likelihood ratio policy gradient from scratch. It's a very interesting derivation. Let's do it slowly. So here's what we're interested in. And we want the gradient of this. So we want the gradient of the utility, gradient of this thing over here. Okay, gradient of a sum is sum of the gradients, so we can bring in that gradient. Just if anybody's not too familiar with gradient notation here, just think of it as derivative of this thing with respect to theta. It's just a vector of derivatives. Then, once we have this, we're going to play a little trick. And this is, we have some foresight why we do this, but it's clear that this is possible. We multiply and divide by the same thing, the probability of the trajectory under theta. Once we did this, we kind of just physically just move some things without really doing any math. Then we remember that the derivative of the log of x is derivative of, the log of f of x is derivative of f of x divided by f of x. Do the same thing here with the probability, but we use it in reverse direction. We say that's the same as grad log probability times reward along the trajectory. So we made a little transition here. The reason we did this, there's two reasons. One reason we can already see on the next line, and another reason will come up later. So first reason we did this is that we now have an expectation here. Expected value under the current policy, this here is sum over trajectories weighted by probability under the current policy. That's an expectation of this quantity over here. Once we have an expectation, as we've seen in Q-learning, we can approximate it by a sample-based estimate of that expectation. That's what we're going to do. To compute an estimate of the policy gradient, we take the quantity that's in the back here, compute it from sample paths we obtained with our policy. I indexes over sample paths. We have m sample paths. So we execute our policy, we find paths, we compute the grad log probability of that path, times reward, average that over all of them, and that's our gradient estimate. I haven't said yet how we compute this quantity here, probability of paths. We'll get to that. But what we see here already is that we have an expectation, and if we can do this, this gives us an estimate of the gradient. Some interesting observations here. This estimate is valid even when the reward function is discontinuous and or unknown. Let's take a step back here. When we thought we're going to optimize this thing here, and you think about, let's take a derivative of this quantity with respect to theta, you might have thought that we would say, oh, derivative of reward with respect to state, then see how the state that you visit depends on your policy pi theta, and have a chain rule effect happening. That's not happening. This is a different kind of derivative. There's no derivatives of reward happening here. It's completely different. As a consequence, even when the reward is discontinuous, we can apply this equation. It's valid. Even when we don't know the reward function, but we just experience a number that's the reward as we roll out, that's all we need for this equation. It also works when you have discrete states and actions. So typically when you think about derivatives, you think we need to take chain rule through things, derivative of this with respect to that, and so forth. If actions are discrete, states are discrete, it might be difficult to do. This kind of derivative works out just fine. So that's really nice. Okay, now let's interpret what's happening here and why this even works. Let's say we have a policy, we do 3 rollouts, and one of them is pretty bad, one of them is medium, and one of them is pretty good. M equals 3. We'll look at this here. So we have 3 different rewards, a good, medium, and bad. For the good reward, what happens is the grad log probability of that path is being increased a lot. For the medium one, it's increased a little bit, and for the bad one, if it's negative reward, it's being decreased. And so what you see here, the way this works is that you update your policy by looking at the probability of paths under your policy, And good paths get their probability increased, bad paths get their probabilities decreased. You can even do this from one sample, actually. It's not going to be a very precise gradient estimate. If you just had one rollout, you could still compute this gradient estimate and do an update to your policy. So tomorrow morning, first lecture tomorrow morning, we'll look at a different kind of derivative, which is a derivative that you're often more used to, past derivatives, that will go through the dynamics model, through the policy, through the reward function and everything. That's a different way of doing this. It requires that you have access to a dynamics model and so forth. We'll see that here we won't need it once we work through the details. But tomorrow you'll see a contrasting method with this one. So for now, just see it as a way of doing it. Don't worry too much about which one is better. That's what tomorrow morning's lecture will be about. Question? Can you explain why exactly does it between data and the probability of non-wrong? Okay, so this quantity here is looking at the derivative of the log probability of a trajectory with respect to your parameter vector theta. If your reward is positive, then this will increase. This is saying if you do an update. So you compute the gradient and I say I'm going to change my parameter vector theta in the direction that the gradient is pointing me to, then the consequences of that change will be that you increase the log probability of the better paths. And in fact, if all rewards are positive, you'll try to increase log probabilities of all paths. But then because the probabilities need to normalize to 1, in practice you won't be increasing it of all of them. The way this all will work out is that the neural net living underneath won't be able to increase probability of everything, and it'll have a higher force for the good ones, a less strong force for the bad ones, and ultimately more increase the probability of the good ones, less of the bad ones, or even decrease the probability of the bad ones. We'll dive more into this in the next few slides. Yes? I'll give you a new derivation of the exact same math where that will stand out very blatantly. Now let's see how we can compute this. So this is the quantity we need to compute. We have a policy, we use it, we get a rollout, and we need to compute the grad log probability of trajectory given that policy. Okay, well, what is the probability of a path? It's the product of the probabilities of next state given current state in action, as encoded by the dynamics model, times the probability of action given state under the policy. Multiply this together over all times. It's like a Markov chain. Multiply it all together. That gives you the probability of that particular path that you experienced. And we need the derivative of that probability with respect to theta. Okay, let's do that. First of all, a log of a product is a sum of logs. So let's do that. Once you have a sum, gradient of a sum is sum of the gradients, so we can bring that in. Why did this term disappear? It doesn't have a theta in it, because theta is the parameterization of the policy, and the dynamics model of the world does not have your parameter vector of the policy encoded in it. It doesn't play a role. So the dynamics model just disappeared. And that's really the beauty of this derivation here, is that you can compute this gradient with only having access to your policy, not having access to the dynamics model that encodes whatever happens in the world. Okay? So no dynamics model required. Very nice. All we need to do is compute the grad log probability of action given state. This is your neural net, right? Your neural net encodes a distribution over actions given state for each state that you encountered. And then you can just backpropagate in your neural net to get out the derivatives. That's what you need for this. Multiply it with reward, you get your gradient contribution. Yes? The p's are different on the left and right hand side. So this p and this p, there's some overloading of notation here. It's fine to think of them as different. Another way to think of it is that p is the general measure over all events that could happen in the world. And if you ask p how likely is a trajectory, it can tell you. If you ask p how likely is the next state given current state in action, it can also tell you. Yes?
This rule added the Markov decision process assumption. What kind of problem doesn't fit the real life?
So the assumption here, Markov decision process assumption, is this thing right here. I mean, that's one of the main assumptions. There's also how the reward is encoded. So this thing here often can be made to hold true by making your state big enough. If your state is big enough, you encode a lot in your state, but in practice, you often want to play games. If you make your state too big, there is too high-dimensional vector, that's your state, then often things are harder to learn. Things become trickier, and often there is a trade-off. And so often, you might not have a perfect Markov model, and you might just do it anyway. And hopefully, it's a good enough approximation. Other things you can do is, this is beyond the scope of this lecture, but you could have, instead of states here, in this derivation, you could actually have just observations, whatever you observe about the world, and a similar derivation can be made to go through. Now then, the policy that you would want in practice, if at any given time you don't observe enough to know the state, you would want a recurrent neural net policy, and a lot of machinery gets a little more complicated, but the same philosophy can be made to work still. I'm going to continue a little bit and then see later where we're on time. Okay, so what we have now, we have a way of estimating the gradient. This was our equation with this new notation, but then we also know when we look at the details again that this gradient here, that this grad log probability of path can be computed with just sum of grad log probabilities of actions given state encountered. So we can do this now. Y likelihood ratio. Here's another way of deriving this. Comes from importance sampling. You might wonder why we're deriving this twice. We already know what we're going to do. This idea will play a role in what John will look at later when he looks at proximal policy optimization, which is probably the state-of-the-art current reinforcement learning algorithm, and might be your first choice if you just throw an algorithm at something. And I'll rely on this derivation. Importance sampling. What is importance sampling? It's something where you compute an expectation under some distribution, namely when you use your policy pi theta. You want to know what the expectation is, but your samples, your trajectories come from another policy, pi theta old. So you're going to sample from pi theta old, which will give you trajectories. You're going to use those trajectories to compute an expectation, but you care about the new theta. And then what you have to do is you have to correct with this ratio here for the fact that you sampled from theta old rather than theta. That ratio performs the correction. This is a way to compute the expectation we care about, but shows it as a way of computing it based on samples from an old policy rather than the current policy.
It seems like there's a very large sample space in which to sample, so actually that probability would be a lot of zeros.
So what you're getting at is that we might need to learn a policy in a high-dimensional space, and a lot of paths could happen. And if you compute an expectation here, it's not like you're going to have seen every path, and every one of the paths is going to contribute, only a few. What we're counting on there is that the neural net that represents the policy is able to generalize across states. And that thanks to that, things you see along one path can allow you to learn things that will also generalize to things you might encounter along another path. If that's not true, then you might indeed need a ridiculous number of samples to get this to work. Either way, it already requires a pretty large number of samples, don't get me wrong. But so what we can then do is we can take the gradient of this quantity. Gradient of expectation is expectation of the gradient under some mild assumptions. Then we can reformat this a little bit again, and then we can evaluate it at theta old. This quantity over here turns out to be the same as what we had before. So what we did here is effectively we did it by the finite perturbation. We said if we're curious about other policies, even if we have trajectories from an old policy, we can understand how good this other policy is going to be. Let's look locally if we deviate from theta old, and it gives us the same gradient. What it also means is that you can, in principle, do more. You can actually also use the original equation to see if you change your policy after your gradient update, you can use this equation to estimate how good that update was, rather than just blindly trusting that your gradient put you in a good spot. And that will come back a lot in John's lecture, is having this kind of extra information about what happens when you change theta rather than just looking at the gradient and taking a step. Okay, so this will come back for entirety of John's lecture, I think. So there could be many trajectories you might care about. There could be a lot of things happening here that lead to what I just showed you while being a valid estimate of the gradient, requiring an impractical number of samples to be able to get a good estimate from this empirical estimate. We're going to introduce 3 tricks to improve this: a baseline, temporal structure, and then in John's part, this latter set of tricks. Okay, let's revisit what's happening here. So what's happening is we have a objective, gradient of the objective with respect to theta. This is the gradient. Following the gradient means increasing the probability of the better paths. But let's think about it very concretely here. Let's say we did 3 rollouts, and all 3 rollouts had positive reward. Then actually what's going to happen is you're going to try to increase the probability of all 3 of those rollouts. But some of these rollouts are better than others. Nevertheless, you're going to increase it for all of them, but just for some more than for others. Really, what you would like is that maybe if something was bad, you would decrease the probability of that rollout. That will happen if you had negative rewards. If a reward was negative, you'd decrease the probability of that rollout. But if they're all positive, that wouldn't even happen. And so you could also already see how this will require a lot of averaging of many rollouts to get the good ones to overrule the bad ones in the update that you converge to by averaging each contribution. Okay, so what can we do to alleviate this? We'll introduce a baseline. Okay, what's a baseline? This was the original equation. Right here, we subtract out b. So instead of multiplying the grad log probability with the reward that we experience, we multiply with the reward minus a baseline. Intuitively, we want increased probability of paths that are better than average and decreased probability of paths that are worse than average. So if we can measure what average performance is by just looking at the rollout, see what the average is, we could call that our baseline. We could plug that in there, and now we've modified this to do what we want, or to be at least much closer to what we want. Can we do this mathematically? Do we still have a valid gradient estimate? It turns out there's a proof from '92, Williams reinforced paper, that shows that when you put this in here, you average over infinitely many trajectories, you still get the exact gradient. So you're not biasing the computation. All you're doing is actually reducing variance. That's a good thing. If you can stay unbiased, reduce variance, that's a gain. It means you need less samples to get a good estimate. Here's some math that proves this. Don't worry about it, but it's in your slides that you can download from Piazza. You might already have them. You can go through it yourself. The thing to keep in mind is that this is okay as long as the baseline does not depend on action. So you cannot have B also depend on the probability of the action that you took here. That's all. But it doesn't, because we just take the average of rewards we got or something, and then that's fine. Okay, we can actually do more. Thus far, we have largely ignored the temporal structure. This is our policy gradient estimate now. But we also know that we can decompose this into a sum of gradients for each time step, this thing over here, multiplied by all the rewards, which is also sum of rewards over time. What we see here is that we have grad log probabilities of actions given state and all the rewards. But why would you change the probability of an action, let's say at the final time step, based on the reward you got at the first time step? Doesn't make sense, right? As you look at this multiplication here, all times, probabilities of actions at all times interact with rewards at all times. Really, you only want actions to interact with future rewards that come after them, okay? So we'll rearrange this. We'll take this out. This is the part that comes before the current time. That part we're just going to remove. Doesn't depend on what action you take at the current time, what reward you got in the past, so it should also not affect the grad log probability update for that action. Do this, removing those terms, we get this policy gradient equation over here, which is the standard policy gradient that you'll see a lot. All right, so it's looking at, I'm going to increase the grad log probability of an action I took given state. And by how much, assuming this is a positive quantity, by how much the rewards experienced from that time onwards, from t to the end, is better than what you would get on average from that time onwards. And if it's worse than average, probability would go down. I'm going to keep going for a little bit. Now let's think about good choices for B. What does it mean to take the average? A constant baseline would be something where you just look at all rollouts and you just average, and that's what you subtract out. It turns out that there's some math that's derived by Williams and also by actually Greensmith and Baxter and Bartlett that shows what the optimal baseline is. It turns out that you should not just average the rewards for each rollout, but you should do some weighted average based on some ground log probabilities of the rollouts, where rollouts that are more likely contribute a little more to your average than rollouts that were less likely. Turns out that's an improvement to the simplest baseline. Admittedly, I don't think anybody uses this because it's not a huge improvement, but if you look at the math and you want to do the minimum variance thing, that's what the math will tell you. You can also make it time dependent, because we saw we have grad log probability of actions given state, not just grad log probability of the entire path. You can make this baseline time dependent and take the average from a certain time onwards. You can also make it explicitly state dependent. You can say, I have seen rewards from state ST. I can then compute a value function, v pi of ST. What's a value function for a policy? It tells you how much reward you're going to get from that state onwards. Actually, that's what we really want, because that value function is telling us how much you would have gotten on average based on your current policy. And then if your action got better or worse, then we want to increase or decrease the probability of that action. Okay. Then, of course, we need to estimate this v pi thing. We haven't really seen yet how to do that, except when we have a transition model, we can run policy evaluation. But here we don't have a transition model. We need to estimate it from samples, be a large state space. We have to do some extra work. So here's what you would do. You would collect a bunch of trajectories under your current policy. And then you would do a optimization where phi is your parameter vector. You're going to have a separate neural net, maybe for the value function, neural net for the policy, neural net for the value function. Value function neural net parameterized by phi. You want this neural net for the state that you experienced to predict whatever rewards you got after you were in that state. So for all experience you have supervised learning data now. You had a state. You see how much reward you got. That's input state, output how much reward you got. That's a supervised learning problem. That's what we're trying to solve here. And so you can run an optimization here to find the best value function for your current policy. You can just farm that off to any kind of standard supervised learning thing that you have, and then use that value function in your policy gradient update. Okay, so this is the Bellman equation for v pi. You can do something else. So this is called the Monte Carlo estimate of your value function of v pi. You can use a TD estimate. What you do there is, as you have experience, you only look at these state, action, next state, reward combinations, and then set up an optimization problem like this. This is saying I want my value function at state S to be equal to immediate reward plus value at the next state according to the current estimate I have for my value function. So phi I is your current estimate of the value function, and you're going to use it. What you see here is based on the current estimate, a target. That's the target value that you compute. And this is the new parameter that you're optimizing for. And then maybe you don't want to move too far too quickly because you only have a small amount of samples. And so you have a good prior that staying where you were isn't too bad. And so that's what this term is over here. So you have different things here to do the same thing. There are pros and cons to either one. This is simple. You just have a clear target anytime you do rollouts and you regress onto it. And it's unbiased, which is nice. It's not very sample efficient. If you want to be more sample efficient, this will often be more sample efficient because it exploits this Bellman equation structure by computing target values and regressing onto it, just like Q-learning. But also it can be harder to stabilize. It doesn't always work out as easily. You might have a lot of tweaking to do to get this to be stable. Yes? How is this different from using a smaller learning rate? There's some equivalence there. This is a way of essentially suggesting smaller steps are better. This prior is saying small step is better than a larger step, but rather than just putting it in the algorithm, we're putting it in the objective. Yes? So what changed? When we looked initially at value iteration, we saw that we needed this P over here, the model. What changed is that we are doing sample-based evaluations of all of this. So we are setting the target. So what this is here is an expected value over what happens at next states. We're going to sample from this. The experience we collect by using our current policy is giving us samples of this thing over here, and we're going to average those samples. And by averaging them, we get the expectation that's here, or an approximation to it. So two alternative ways to do this: Monte Carlo approach to estimate the value function, or the TD approach that uses target values and iterates and get better and better value function this way to get the value function. Let's look at a full algorithm. This is the vanilla policy gradient algorithm. I think this will be part of your lab 4 that you'll work through tomorrow. You initialize your policy, let's say your big neural net, some parameter vector theta. You initialize your baseline. We've seen many options for the baseline. Probably estimating a value function is the natural thing to do. Then you iterate. What do we do in an iteration? We update the policy. Every iteration will lead to a better policy, hopefully. In practice, it's a stochastic procedure, and sometimes you get worse, sometimes you get better, but on average, you keep getting better. What do we need? In an iteration, we collect a bunch of trajectories. That means we execute the current policy, just get data. Then, along each time step in a trajectory, we compute the returns that we got from that time onwards. And we actually discount them. Okay? For now, you can assume discounting is 1, but actually, it's often good to discount here to reduce the variance on this quantity. Just as a variance reduction trick, not because you want to discount, not because you think interest rates or whatever affect when you need to get rewards, just because this could be a large number of terms you're summing together, and it could have very high variance, and discounting can reduce that. Then you make an advantage estimate, which is you look at the reward that you got along the rollout, and you subtract out the baseline at that state, ST. Okay? That's exactly what we've been seeing on the previous slides. That's computing this quantity over here. That's the baseline, and then this is the sum of rewards from there onwards. After we've done that, we refit the baseline. That's just recomputing our value function based on the data we've seen so far. This one over here does it based on Monte Carlo because we have the actual rewards here and we try to fit to the actual rewards. You could also use the TD thing, up to you. Then, at this point, we can compute our policy gradient estimate based on the quantities we have computed. G hat, which will be this quantity over here, summed over all times and all states and actions that we encountered. Then we take a step in that direction. We have some step sizing, of course, to make sure we don't step too far. And then we repeat. That's the algorithm. So it's actually very simple. It's not that many lines of code. And actually, Andre will show some code in his presentation to dive into it at the Python level, what this actually does. So the baseline is updated over here. Refit the baseline. And the way it's written here in this algorithm is using this estimate, the Monte Carlo version. But other versions could be used like this one, like the other one if you want to. OK, so what do we have now? We have this gradient estimator. We've looked at how to build an algorithm around it. We haven't yet. I'm going to keep going for the interest of time. And you can post a question on Piazza if you want, and the TAs are following along with those questions. This here is really, what we really would want is actually the Q value for that state in action, rather than just an estimate from one rollout. Because on average, we're going to get the Q value. So can we get something closer to that is a question you could ask. Okay? If we just use the rollout, it's going to be high variance. So we already reduced the variance by discounting. We could reduce it even more by introducing function approximation. So discounting, very straightforward. We've seen that. Just introduce discounting. That gives us a better estimate, not a better estimate per se, but a lower variance estimate than without discounting. How about function approximation? Well, the expected value of all rewards that we might get is expected value of reward followed by expected value of the value we get at the next state. Okay? So we could actually replace this sum of all rewards by just reward that we get immediately in that rollout plus value at the next time. We could also take 2 steps of rewards and value at the next time, or 3, and so forth. A3C, one of the state-of-the-art policy gradient methods, uses exactly this idea. You pick, let's say, k equals 5, and so instead of using sum of all future rewards, you use the first 5 that you encounter, followed by your value function estimate. Okay? So now you're using your value function estimate twice. You're using it to replace this thing over here with sum of 5 rewards and then value function, and you subtract out value function at the current state here. Okay? So here's a complete algorithm that does something like this. Oh, I skipped a variant. Hold on. So A3C picks a specific step size. You can do something else too, something called generalized advantage estimation. Does an exponential averaging of all possible choices of k that you could pick. Do lambda-based weighting, and you get the average of all of those horizons together. It's equally efficient to compute, and it might be an easier way to kind of get what you want rather than choose one specific number of steps. It's very related to TD lambda, which you can read about in the Sutton and Bartow book. So this is Actor-Critic now. What does it mean to be Actor-Critic? It means that you are running a policy gradient method where you estimate a value function for your baseline. Once you have a value function for your baseline, it's not called policy gradient anymore, not necessarily. You can choose, you can still call it that, but the technical term would be Actor-Critic at that point. So we have an Actor-Critic method now. We have a current policy, current value function estimate for that policy. We collect rollouts, we collect accumulated rewards along the way, and then this could be based on the A3C method, could be based on generalized advantage estimation. You have it here, you refit the value function, and you do your policy gradient update based on it, and you repeat. And again, you have a lot of choices in terms of do you use Monte Carlo versus A3C cut off after a few steps, or generalized advantage estimation. You have those choices both when you look at the first term here in the policy gradient method, what you do there, as well as here when you refit your value function. So a lot of orthogonal choices to make. If you do this, it actually works quite well. So A3C achieved state-of-the-art results for Atari and also really good results in continuous control environments. Better than DQN in terms of how fast it gets somewhere as a function of wall clock time. There's a few reasons for this. One of the reasons that is also there that there's a little bit of built-in exploration by running it over multiple machines, and the machines are not perfectly synchronized, and as a consequence, they run slightly different policies, and that's related to the parameter noise that Vlad talked about in his very last slide. So you get very good results. You can even do things like learning to navigate a labyrinth. So what's underneath here is a neural network that's a recurrent neural network, because all you get is images, and from just the images, it's not going to be possible to decide what to do. You need to retain memory of what you've seen in the past. The recurrent neural net encodes the policy, so the policy knows how to remember what you've seen in the past. A good policy knows that, and can then have you navigate towards the good rewards that might look like apples or cherries or watermelons and so forth. This is pretty amazing here. This is taking in monocular images, right? Doing low-level control, taking just monocular images, and effectively building a map of the environment it's in. And nobody built into it what it means to build a map. It just learned that a neural net, a recurrent neural net that does something equivalent to map building, happens to be a good policy and can be used to do things like that. There are some tweaking parameters with this. When you do generalized advantage estimation, there's lambda, how do you exponentially decay the horizons that you work with, and there's gamma, the discount factor. Turns out that if you study lambda, what happens is you see that effectively you want to be really close to Monte Carlo estimates of your value function and for your rollouts, and only bring a little bit of TD into the equation. Okay? but bringing a little bit of TD will reduce the variance and help. Once you rely too much on TD, things will get biased and things will not work nearly as well. Gamma, and same for gamma, you want to tweak your gamma a little bit. So lambda, we see here lambda 0.96 is good and gamma 0.98. Keep in mind that does not mean that we change gamma for the problem definition and we say, if we change the problem, can we do better? It's the problem remains gamma equals 1, and we evaluate on how well the policy does when gamma equals 1, but we train with gamma something different than 1 and see which choice ends up doing better. So let's see what we can do learning-wise when we use, this uses something John will cover in his lecture that improves the gradient step a little bit by using a trust region. Combines that with everything we've seen here. What we're going to watch is a neural net controlling this humanoid. The neural net gets as input joint angles, joint velocities, outputs torques at each of the motors. The reward function is as simple as the further, it's different, okay, further that way, the better, and the less impact with the ground, the better. Very simple reward function, nothing in there about walking should look like this, just distance covered and impact with the ground should be minimized. Neural net has about 100,000 parameters. Iteration 0, what do you expect? Randomly initialized, it's not going to know what to do. It's probably going to fall over. It'd be very surprising if your random initialization knew how to control this robot. It can happen. Very low probability, though. Never happened to us. So let's see what happens. Indeed, it falls over. But it's a random policy. It does different things. It'll make more likely the things that were better than the things that were worse. And over time, improves the policy to actually cover more and more ground. After 640 iterations, it's able to learn to run. Has learned to run. In real time, if we ran it on a real robot real time, it was the exact same robot that behaved exactly like this robot, let's say, 2,000 iterations would take 2 weeks. So not totally crazy. Of course, running it on many machines, it only takes a couple of hours. Here, exact same algorithm, no change, and can learn to control this robot. So what's interesting here is that traditionally, if you work in robotics, you would think about things like, how do you balance a robot? What does it mean to lose balance? What does it mean to have dynamic stability and so forth? And people would think a lot about those concepts to try to design controllers for these robots and then rethink things for another robot. No rethinking needed here. What's the reward function here? Distance of the head to standing head height. The closer to standing head height, the better. And you see, sitting is better than standing. And actually figures out how to get up. Question there?
Yeah, you said it takes 2 weeks on a laptop, but a couple hours, and what size is laptop?
Okay, so timing-wise, what I meant to say, but maybe I didn't say, is it takes 2 weeks if you were to run this on a real robot. If you think real-time experience. So we run it in Mujoko, which is a simulator built by Emil Todorov at the University of Washington. That simulator is designed to run faster than real time, and we can run it in parallel over many processes if we want to. But if you look at the real-time experience that would correspond to this, if we put it on a real robot, it would take 2 weeks. So that's not too crazy. Now, reality check. If you were to do this, for sure the hyperparameters that we used are not going to be the right ones for the real robot, so you might have to run it again. You might not want to run it for 2 weeks to then change some hyperparameters and go again. You probably want to stop a little sooner when it's not making progress. But a lot of these will kind of make almost no progress for a very long time and then finally start shooting up. And unless you kind of wait long enough to know if you've reached that point where they would start shooting up, then you don't know if you have the right hyperparameters or not and so forth. So it's a little tricky. I wouldn't yet recommend running it on a single real robot and expect that in a reasonable time you get a result, but I also feel like this means that we're maybe only a few breakthrough papers away from getting there. Oh, of course, and we did. Yeah, and we did, right? so we run it faster. We run it much faster than real time with this research. I'm just trying to give you a picture of, you see this in simulation, and maybe you have a physical robot at home or you want to build one, and you're wondering, should I use this? And I'm saying, well, maybe. Yes? Yeah, so a lot of research goes in that direction. I'll rephrase the question as I'm answering it. So can you leverage what happens in simulation to learn faster in real life? That's what you would do. You wouldn't learn from scratch in the real world. I mean, you might just for kicks and for research purposes, but if you actually wanted to deploy something, you would first train in simulation, and then you would fine-tune on the real system. And if your simulator was somewhat matched, that could work well. And people are still researching how to do this really right. But ideas that people play with is things like randomizing your simulator and learn a policy that works across many simulators, because if that's the case, then it might also work in the real world, or it might be a robust policy that works in many situations and might be easier to deploy. Yeah, I just want to contrast this with some real-world robots. This is from 2015, I believe, Darpa Robotics Challenge. A lot of people probably have seen this video, and the point here is not that this is the best walking robots that have ever existed, but the point is that these people worked for about 2 years to try to compete really hard in this challenge with a lot of very smart people, and still these kind of failures happened. So what that shows is that this remains a hard problem. Like, robot locomotion is not a solved problem at all. All right, I'm going to stop here. Thank you. And I think I have time for one question while Andre sets up his computer. Yes?
How do you go from learning, talk a bit about this.
I'll stop this so you can ask a question.
Going from learning how to run to being able to train a robot to a goal, right, other than running forward.
Okay, so the question is, let's say you have this robot that has learned how to run. How do you now make it go to goals? So a natural way to do this is to set up your problem a little differently. So you would set up your problem with taking as input state and a direction that's desired or a goal that's desired to go to, and you'd consider that part of the state. So you augment your state space with the goal that you want to achieve. At that point, your neural net can learn what to do as a function of both state that you're in and goal that you're trying to achieve. And so actually you can do this in pretty clever ways also to speed up learning. So recently at OpenAI we had a paper called Hindsight Experience Replay. Marcin Andrićević is the first author on that. And that actually, on top of having the neural net take in goal and state to learn something more general, it also, after the fact, in the replay that happens in the optimization during the Q-learning that's happening there, changes the goal that is fed into the neural net to the one that you actually achieved. So maybe you want to go buy pizza, but you end up in the ice cream store, and you bought ice cream. Then you might say there is no reward associated with this. Or you could say, if just my goal had been to buy ice cream, I would have achieved high reward and I would get great signal. And so that's what Hindsight Experience Replay does to get signal into your reinforcement learner, which is often the really hard part, to get non-zero reward or good signal to learn from. All right, thanks again.